Okay, just 2 more minutes and then we'll start this next lesson. Thank you, Amanda. Have breakfast. Oh, good.
Just a protein bar.
It's not breakfast, man. Breakfast is like a bowl of oatmeal. Do you know oatmeal?
Yeah.
Yeah.
But it's kind of equivalent to protein bar.
Protein bar. I only ever tried those protein drinks twice in my life, and both times I was sick afterwards. Yeah, don't like them at all. Those like protein smoothies. Oh, no good. No good. Okay. Did you get a couple of these done? Yeah, which one are you on, Siba? Wonderful. Yeah, you can try that tonight then. Matt? Yeah, it's a good one, isn't it? Yeah, I like it. Okay, so let's start the next lesson now. If we can write this down. Resistance and resistors. Got that? Yeah? Okay. So, couple of things to talk about, but not too much. Again, not so difficult since we're just starting a new chapter. So, if you look at your formula in the last class, what did I say charge is equal to?
Current.
Yeah, I said that the charge is the current multiplied by the time. Yeah? So you could actually rewrite this as current is charge over time, or in other words, charge per time. In fact, you can kind of think of it almost like this. Something you did in maths class today. So I guess what I'm saying is current is a little bit like velocity. You know, velocity is speed over time, meters per second. Current is kind of the same thing. It's like charge per time, coulombs per second. So you can think of 1 amp as like 1 coulomb per second. It's like a speed nearly. Okay. So this is another definition of current. It's a simple definition. Current is the rate of change of charge per time. Okay, so if you can write that definition down, and there it is as a formula. Terrible, isn't it? I cycled today. Just like back home, huh?
It never rains.
You're from Sudan, isn't it?
Yeah, but
Yeah.
inside it never rains. So then
Yeah. Yeah? Well, the nice thing about the rain is this morning I saw a rainbow over the school. You know a rainbow, don't you? Yeah. I didn't know if this is something that you ever get to see back home.
No, you do see it quite often.
Yeah?
I don't know, in Dubai.
No, well, firstly it has to rain first.
Rain.
It doesn't rain too often in Saudi, so not going to have much chance to see it.
It rained this
Not,
year.
not too
Oh,
often.
this year,
Yeah,
okay.
when I left.
Every year.
Yeah.
Okay, so now on to a new definition. Oh yeah, so Andek, your plug said 0.5 amps. So that means in 1 second, half a coulomb of charge moves through the plug. Okay. Oh, now it's really raining. Oh, pleasant. Okay, so definition now. We have this thing called voltage. And voltage is like potential energy for electricity. So when we say voltage, we're actually talking about joules per coulomb. So 1 volt is 1 joule of energy per 1 coulomb of charge. So imagine I have 1 coulomb. This is 1 coulomb of charge. And it moves in 1 second. How much current is that? 1 amp, okay? If I say this is under 1 voltage, what I'm saying is that this can do 1 joule of work. Now you might say, what work can it do? Well, Andek can tell us, because on his plug, you can see what the work is being done. It's charging your phone, you know. So if we say this coulomb has 1 voltage, under 1 voltage, it means it can do 1 joule of work. Now that's important because we like electricity, because it can do work for us. Okay? So voltage is like potential energy. 1 volt represents 1 joule per 1 coulomb. So a volt is like a joule per coulomb. That's what a volt is. Okay, so now you need this definition. So, if we had a big voltage, it would be correct to say that we could have lots of work per coulomb. Okay, got that? Yeah? Yeah, continue? Okay, so next one now is resistance. So we talk about resistance as being a hindrance to the current. It's a measure of the difficulty it is for the current to pass through the conductor. So you know some things are good conductors and some things are bad conductors. Like copper is a good conductor. What's a bad conductor? Wood is a bad conductor. So these materials have different resistance. A low resistance is good for the current. A high resistance is bad. What precisely is resistance? Well, we measure resistance in a unit called ohms. Who knows what this letter is here? Omega, good, yeah. And what exactly is an ohm? Well, 1 ohm means 1 volt of energy was converted into something like sound, light, or heat when 1 amp passes through it. So, again, if I go back to my rubber here, so this is 1 coulomb, and it has 1 volt. So if it has 1 volt, how much energy does it have? 1 joule per 1 coulomb, okay? If this hits a resistor, and maybe it turns into heat or something, and it loses its energy, then we say if it lost 1 volt per 1 amp, then we say it's an ohm of resistance. Losing your 1 volt of energy per 1 amp, that's a resistance of 1 ohm. Yeah, so you need the full box. Okay. So in the example of Andek's phone, it has a resistance because the current that has the voltage that does the work, when it passes through his phone, that work from the current is gone into the phone in, like, making the phone light up and do lots of things. Continue? Yeah. So, there's a relationship between voltage, current, and resistance. The 3 of them are related. And I find this picture helpful to explain the relationship between VI and OR. Okay, so this is my picture I found on the internet. I thought it was funny, so I'd include it. So let me explain it. You know these people, don't you?
Mm-hmm.
You've seen them before on the internet. Yeah, okay. So, you can see that the resistance is like this guy. He makes it difficult for the current to pass through. And who's doing all the work? The voltage. Okay? So, if this is big, what would he have to be? Big as well. Okay? And you can see that he is wasting his work when the resistance is big, because he's converting his work into just pushing the current through. Yeah? So I don't know. I thought this was cute. So this is a simple relationship between them to have a picture in your mind. So if we're talking about the relationship between the 3 of them, we'll need a way to measure the current, the voltage, and the resistance. So we can measure voltage by using a voltmeter. And here's a picture of one. So this is how we can measure voltage. Now, I should say, you can only measure voltage between 2 points. So, just to draw a picture here. Okay. Come on, where's my pen not working? I go. Alright, so right. So here's my electrons, and they're moving along. And maybe I'll have something here like I'll put a light bulb. So the light's coming off here. Right, so the electrons, let's say the electrons are moving to the left. So which way is the current? To the right. The current is here. To the right. Okay. Now let's just keep it simple. Let's say it's 1 amp. And we'll also say it's 1 volt. So for every coulomb of charge, how much work is there? 1 joule. 1 joule per coulomb, which we actually call for every, what did I just say? Yeah, every coulomb, sorry, that's stupid. Every coulomb has 1 joule of work it can do. Now, when it passes through the light, can it still do this work afterwards? So, imagine here's my charge, and now it is over here. Does it still have the ability to do 1 joule of work? No, why not? Because the work was converted into light. Yeah, so now the energy is here as 1 joule. Okay, so the voltage has dropped. Instead of doing 1 joule per coulomb, it now can't do anything because it was converted. So you can connect a voltmeter here, and you can connect it here, and when you connect it up, it will say 1 volt. This means 1 volt was lost. 1 joule was lost between point A and point B. We could do 1 joule per coulomb, but now we have 0 joules per coulomb. No more ability to do work because the work was converted into light. Okay. So my point is the voltmeter, you have to connect it between 2 points, and you can see how much the voltage has changed between the 2 points. Has it gone up or down? Okay. So I think you could just write down this sentence. We can measure voltage by using a voltmeter.
Picture?
Nah, it's okay. Okay, you got that? How can we measure current? What could we use to measure current? That's it, yes, isn't it? An ammeter. So we can measure current by using an ammeter. What do you think an ammeter looks like? It looks like this. So this is how we measure an ammeter. This is how we measure current. Okay, we can measure current by using an ammeter.
An ammeter.
Is the start of ammeter a vowel sound?
Oh.
I know it's obviously a vowel because it's, well, it depends how you pronounce it. Tell me this. Do I put a or a in front of this word? Yeah, because it has a vowel sound. Is there a vowel sound here? Ammeter.
It sounds wrong to say ammeter.
Does it? Sounds right to me. An ammeter?
Using an ammeter.
I don't know. Anyways, for the ammeter, you put it in the wire, so to speak, in the circuit. So you would have your electrons, and the electrons move through. It's almost like it counts the charge as it passes through. So it might say something like 1 amp, or 2 amps or whatever. So it counts. It's like a counter nearly. It counts the charge as it passes through. So you don't need to connect it to 2 points like the voltmeter. You just connect it to 1 point. There's like an in and an out. So in the picture here, what you do is you connect it here in the black one and in one of the red ones. Now the reason for this picture having 3 connections is if you're using a small, a medium, or a large current. Because if you use a large current in a small measuring device, it'll blow it. Okay, so there's 2 points, like an in and an out. Okay, tell me how we might measure resistance using. Now think about what we did with the previous two. The language, voltmeter, ammeter. So we'll measure resistance using a. No, you're not thinking. We measured voltage by using a voltmeter because the unit for voltage is volts. Yeah, so we measure resistance using a ohm meter because the unit for resistance is ohms. So we measure resistance by using an ohm meter. You could probably guess what the picture looks like for an ohm meter. That's right. Yeah. Well, I mean, not that they're rare, but they're rare to use because they're actually very inaccurate. They're very inaccurate. No, I don't mean that this is inaccurate. I mean all ohm meters are inaccurate, even modern digital ones. Measuring resistance is actually very difficult to do, and you will have to do an experiment to measure resistance accurately. And in fact, there's other ways to measure resistance without using an ohm meter, because ohm meters don't measure accurately as voltmeters or ammeters do. And there's many reasons for this, we'll do that in time. Okay, continue. Yeah. So, we will not use or study the ohm meter because it's not actually accurate. We'll talk mostly about measuring voltage using the voltmeter and measuring current using the ammeter. Oh look, I put AN here. That's interesting. An ammeter requires a current to flow through it. A voltmeter you use between 2 points, and we talked about this already. Okay, I already drew that, fine. Now, there is a relationship between voltage, current, and resistance. And the relationship, I spelled triangle wrong. The relationship is in this triangle. So, if you want the voltage, that's equal to the current multiplied resistance. If you want the current, what's that? Voltage of resistance. And what about if you want the resistance? Yeah, so if you want the resistance, rather than using the ohm meter, you can actually use the voltmeter, the ammeter, and divide. It's actually more accurate. So if you can add this VIR triangle. What triangle does this remind you of? Well, true, but another triangle I did with you. Speed, distance, time. Okay, got that? Triangle? Yep. Now, It's not that difficult. Let's have a look at a simple example. An ammeter measures 250 milliamps. The voltmeter measures 220 volts. What is the resistance in the light bulb? Okay, so I have current and I have voltage and I want resistance. So, what's my formula for resistance? V over I. So in this one it would be oh my goodness, what happened? 220 over 0.25 because it's milliamps. Alright, can you calculate that please? So 220 over 0.25. So the resistance of the light bulb is 880 ohms. Okay. Okie dokie? Is that okay? It's not too bad, right? Just using this triangle. Right. Here's another one. We'll do this one together. A 6-volt battery is used to power a toy which has a resistance of 2 ohms. What is the current? Okay, so give me the current, please. Use your triangle. Tell me what the current is. The I. Yeah, how did you calculate it? V over R. 6 over 2. So 3 is the answer for the first one. Is that okay? Yeah? Right, part B. If the toy is left on for 1 minute, then how many electrons flow from the battery into the toy? Okay, so if the toy is on for 1 minute, we want the number of electrons. What formula could I use for B? What formula could I use? Good. Q equals IT. Now, what's the I for this question? 3. And the T, 1 minute? 60. So that's 180 coulombs is the charge. But I want to know how many electrons. So remember, 1 electron is, what did I say was 1.67?
1.6 times 10
minus
9.
9? 19.
19.
Okay. So how can I figure out how many electrons I need if I need this much charge? Oh, what was it, 1.6 just? Okay. Right, how can I figure out how many electrons?
Times by 180.
Divide. 180 divided by 1.6 times 10 to the minus 19. So that's how many electrons there were that moved. So what's that?
1.1 times 10 to the power 21.
Oh, sorry. Well, it's still a big number, huh? So you can see that even a small battery turned on for only 1 minute will send 10 to the 21 electrons through the toy to power it. It's a lot. Okay. If the battery is replaced with a 12-volt battery, then how does the current change? You may assume that the R is constant. Okay, so did we calculate the R?
That's 2.
Oh, it's told in the question it's 2. Okay, so the V is now 12 volts. This is 2, so we want the I. So what's the I now? 6 amps. And what was it previously? It was 3 amps, wasn't it? Now it's 6 amps. So the current has gone up. Yeah, that's all for this one. That's it. So for this lesson, you really just need 2 formulas. This one and this one. And that's all you need. Okay. So what time are we at? Oh, good. So if we can try these for about 10 minutes or so, and then we'll finish.